Welcome to your deep dive. Today, we're going to be tackling a new theory in physics.
Oh, wow.
It's called the quantum tensor field,
Okay.
and it's pretty ambitious.
Sounds like it.
It's aiming to solve some of the biggest mysteries in the universe,
Like,
dark matter and dark energy.
right.
And our main source for this is a research paper published just this year,
Okay.
January 1st, 2025,
Oh, wow. Just out.
by physicist Kenny Lujan Rodriguez.
It really is a fascinating paper.
Yeah.
Physicists have been trying for years to reconcile Einstein's theory of general relativity,
Right.
which works great for large-scale gravity,
Mm-hmm.
with the world of quantum mechanics,
Yeah.
that governs the tiny particles.
Right.
The problem is these two incredibly successful theories just don't seem to agree.
So it's like having two sets of rules
Yeah.
that work perfectly in their own domains,
Exactly.
but clash when you try to combine them.
Exactly.
Yeah.
And this clash causes real problems. When we try to explain things like how galaxies rotate,
Oh, okay.
they spin much faster than they should based on the visible matter alone.
Which is where the concept of dark matter comes in, right?
Precisely.
This invisible stuff that supposedly provides the extra gravity to hold galaxies together.
Yeah. And then there's dark energy,
Right.
this mysterious force that seems to be pushing the universe apart at an accelerating rate.
Mm-hmm.
We've never directly observed either of these things.
Right.
They're more like placeholders for something we don't understand yet.
Okay, so that's the problem.
Yeah.
Now, how does this quantum tensor field theory attempt to solve it?
Well, what's fascinating about Rodriguez's approach is that he proposes a kind of force field
Okay.
called the tensor field,
Mhm.
which behaves differently depending on the strength of gravity.
Oh, okay.
Imagine it like a fabric
Okay.
woven into the very structure of space-time.
So is it like an invisible web that stretches and interacts with everything in the universe?
That's a good way to think about it. Now, in regions of extremely strong gravity,
Mm-hmm.
like near a black hole,
Yeah.
this fabric essentially tightens up,
Okay.
and gravity behaves exactly as Einstein predicted.
Okay.
And here's where it gets really interesting.
Okay.
In areas with very weak gravity,
Mm-hmm.
like the vast spaces between galaxies,
Yeah.
the tensor field starts to behave differently.
Oh.
It's like the fabric loosens up and starts to vibrate.
Hold on.
Yeah.
Vibrating. What does that even mean in this context?
Imagine a guitar string.
Okay.
When you pluck it,
Yeah.
it vibrates at a certain frequency,
Right.
creating sound waves.
Mm-hmm.
Similarly, Rodriguez suggests that in regions of weak gravity, the tensor field starts to oscillate
Okay.
or vibrate
Yeah.
at specific frequencies.
Okay. I'm starting to see where this is going.
Yeah.
Are you saying that these vibrations might actually be what we're perceiving as the effects of dark matter?
That's exactly what Rodriguez proposes.
What?
He suggests that these oscillations of the tensor field create an additional gravitational pull
Right.
that helps hold galaxies together,
Okay.
eliminating the need for invisible dark matter particles.
Wow, that's a pretty radical idea.
Yeah.
Instead of adding something new to the universe,
Why
it's
not?
saying that a property of this existing field could be responsible for what we observe.
Precisely.
Okay.
And it's not just a hand-wavy idea either.
Yeah.
Rodriguez has actually done the math.
Okay.
And his theory makes specific predictions that scientists can test.
Right.
It's a more natural extension of what we already know about gravity,
Okay.
compared to some other theories out there that rely on tweaking the laws of physics.
So instead of patching up the existing rules,
Okay.
it's offering a more fundamental explanation.
Exactly. And remember that symbol I mentioned earlier?
Uh-huh. Okay.
Yeah. That's the mathematical representation of this tensor field.
Okay.
And by incorporating it into the equations of general relativity, Rodriguez has been able to make some pretty remarkable predictions.
Let's unpack some of those predictions.
Oh,
You
yeah.
mentioned that the theory is testable.
Right.
What kind of experiments are we talking about?
One exciting avenue is through the study of gravitational waves.
Okay.
Those ripples in space-time
Yeah.
caused by massive events like black hole collisions.
Right.
Rodriguez's theory predicts that the tensor field would interact with these gravitational waves in a unique way.
Like throwing a rock into a pond and watching the ripples interact with the vibrations of a string submerged in the water.
That's a great analogy.
Yeah.
Instead of smooth ripples,
Okay.
we'd see specific patterns or modulations in the gravitational waves
Gotcha.
caused by the vibrating tensor field.
So scientists would be looking for those telltale signs in the data collected by instruments like LIGO,
Exactly.
which detects gravitational waves.
And there are other possibilities too.
Okay.
Rodriguez suggests that the tensor field could also be detected by measuring tiny gravitational variations near asteroids,
Oh, okay.
or by studying the dynamics of binary star systems.
Interesting.
We suddenly have a new set of lenses to look at the universe with.
That's amazing.
Yeah.
So this theory isn't just explaining things we already know.
Right.
It's opening up entirely new avenues for exploration and discovery.
Exactly.
But we've been focusing on dark matter.
Right.
Does this quantum tensor field have anything to say about dark energy?
It does.
That force pushing the universe apart.
Remember how the tensor field is always vibrating?
Yeah.
Even in the emptiest regions of space.
Right.
Well, those vibrations contribute to the energy density of the vacuum itself.
So even in seemingly empty space,
Yes.
there's this underlying energy field that's constantly fluctuating.
Precisely.
Wow.
And Rodriguez suggests that these fluctuations could be contributing to the accelerated expansion of the universe,
Okay.
offering a potential explanation for dark energy.
Wow. So this quantum tensor field theory is like a 2-for-1 deal. It attempts to explain both dark matter and dark energy with a single elegant concept.
It really is remarkable how it connects these seemingly disparate phenomena in such a natural way.
Yeah.
But it's important to remember that this is still a very new theory.
Sure.
There's a lot more research and experimentation to be done
Of course.
before we can say for sure whether it holds up.
Of course, that's how science works.
Right.
It's all about testing,
Yes.
refining,
Yes.
and constantly pushing the boundaries of what we know.
And what's so exciting about this theory is that it provides a roadmap for how to do just that.
Yeah.
It's not just a theoretical exercise.
Right.
It offers concrete ways to test its predictions and potentially revolutionize our understanding of the universe.
This is what I love about these deep dives.
Yeah.
Getting to explore cutting-edge science
Mhm.
and grapple with these mind-bending ideas.
Right.
Now, I know we've got Rodriguez's paper as our main source, but did you come across anything else that offered a different perspective on this quantum tensor field?
I did, actually.
Uh-huh.
Okay, there was an interesting piece that compared this theory to some other attempts to solve the dark matter and dark energy puzzles.
Perfect. Let's dive into that in the next part of our deep dive.
Oh, yeah?
We'll see how the quantum tensor field stacks up against other contenders in the cosmological arena.
So you're interested in seeing how this quantum tensor field measures up against other theories out there. It's a fascinating comparison
Exactly.
because it highlights just how different these approaches can be.
It's like having different teams of detectives trying to solve the same mystery, each with their own unique methods and clues.
It's a great analogy.
Yeah.
One of the most common alternatives is something called modified Newtonian dynamics,
Okay.
or MOND for short.
Right.
It tries to explain those weird galaxy rotation curves we talked about
Yeah.
by tweaking Newton's law of gravity.
Oh, okay.
It was essentially saying that gravity behaves differently at vast distances.
So instead of invoking invisible dark matter,
Right.
MOND just changes the rules of the game.
You got it. But the quantum tensor field doesn't do that.
Right.
It sticks with Einstein's general relativity
Mm-hmm.
and introduces this new element, the tensor field,
Right.
which interacts with gravity to produce those same effects.
It feels like a more elegant solution, doesn't it?
Yeah.
Instead of changing the fundamental laws of physics, it adds a new layer of complexity that might actually explain things more naturally.
Precisely.
Huh.
It's a more fundamental approach,
Right.
getting to the root of the problem rather than just adjusting the symptoms.
Okay.
Now, another interesting comparison is with loop quantum gravity,
Okay.
a theory that tries to quantize gravity itself.
I remember reading a bit about that.
Yeah.
It imagines space-time as a network of tiny interconnected loops, almost like a microscopic chainmail armor.
Exactly.
How does the quantum tensor field differ from that?
Well, the quantum tensor field doesn't try to quantize space-time itself.
Okay.
Instead, it introduces this new quantum field
Okay.
called the tensor field, which interacts with gravity in a way that could explain those large-scale effects that we see.
So it's adding a new player to the cosmic game
Yes.
rather than changing the game board itself.
That's a great way to put it.
Yeah.
And what's particularly compelling about the quantum tensor field
Yeah.
is that it offers more concrete pathways
Right.
to experimental verification
Right.
compared to some of these other theories.
Yeah, we've talked about the potential for detecting its signature in gravitational waves.
Right.
But Rodriguez's paper lays out some other intriguing experimental possibilities too, right?
Absolutely. He proposes sending probes to asteroids
Oh, wow.
to measure those tiny gravitational variations we discussed earlier.
Okay.
Asteroids are perfect because their own gravity is so weak,
Right.
allowing us to isolate those subtle effects of the tensor field.
It's like setting up a super sensitive microphone in a silent room to pick up the faintest whispers.
Exactly.
What else does he propose?
He also suggests studying binary star systems, looking for tiny wobbles or deviations in their orbits.
Right.
That could be caused by the tensor field.
So by carefully observing these systems, we might find those telltale signs of the tensor field's influence.
Exactly. And he even suggests looking for patterns in the cosmic microwave background radiation,
Wow.
the afterglow of the Big Bang.
Right.
That could have been imprinted by the tensor field in the early universe.
So it's not just one or two experiments.
Right.
This theory opens up a whole buffet of experimental opportunities to test its predictions.
It does.
That's incredibly exciting.
It really is.
Yeah.
And the fact that Rodriguez has gone to the trouble of outlining these possibilities
Mm-hmm.
so clearly speaks volumes about his confidence in the theory's potential.
Right.
He's essentially providing the roadmap for future research.
It's like he's throwing down the gauntlet, challenging the scientific community to go out there and explore these uncharted territories.
Yeah.
Now, you mentioned earlier that you dove into Rodriguez's paper.
Yes.
What were some of the key takeaways that stood out to you?
Well, apart from the experimental proposals we've discussed, what struck me was the depth and rigor of his mathematical framework.
Yeah.
He starts by carefully laying out how he extends the equations of general relativity
Right.
to incorporate this new tensor field.
Yeah, I was particularly fascinated by the concept of effective mass that he introduces.
Oh, yes.
Can you explain that a bit more?
Yeah.
I know we touched on it earlier,
Yeah,
but it's such a crucial part of how the tensor field behaves.
of course.
Yeah.
Think of the tensor field as having different personalities,
Okay.
depending on where it is in the universe.
Right.
Its effective mass determines how it interacts with gravity.
Okay.
In regions of strong gravity,
Mm-hmm.
like near black holes,
Yeah.
its effective mass is high,
Okay.
and it's basically suppressed.
Okay.
That's why we see those classical effects of general relativity.
But in regions of weak gravity, its effective mass decreases
Yeah.
and it becomes much more expressive, right?
Yes.
That's when those quantum oscillations start to kick in.
Exactly.
Okay.
And that's how the theory bridges the gap
Right.
between the classical world of general relativity
Mm-hmm.
and the quantum world.
Right.
It seamlessly transitions between the two,
Yeah.
depending on the gravitational environment.
It's like the tensor field has this dual nature, adapting to its surroundings and playing by different rules depending on the company it keeps.
That's a fantastic way to put it.
Yeah.
And what's so elegant about this
Yeah.
is that it allows the theory to explain those galactic rotation curves
Right?
without invoking dark matter particles.
Right.
Those oscillations caused by the lower effective mass in low gravity regions
Yeah.
create the extra gravitational pull we observe.
It's like the tensor field itself provides the missing ingredient, the
Right.
invisible hand that shakes the cosmos.
Precisely. And that's not all.
Okay.
Rodriguez goes into great detail about how these oscillations would interact with gravitational waves.
Right.
He predicts specific modulation patterns,
Yeah.
a kind of fingerprint that could reveal the presence of the tensor field.
So it's not just about detecting gravitational waves anymore.
Right.
It's about analyzing the subtle variations within those waves
Yes.
to see if they match the predictions of the quantum tensor field.
Exactly. It's taking gravitational wave astronomy to a whole new level.
Right.
And remember those fluctuations in the vacuum of space we talked about earlier?
Uh-huh.
Well, in his paper, Rodriguez explains how those fluctuations
Yeah.
caused by the tensor field's constant vibration
Right.
could contribute to the energy density of the vacuum itself.
Which, if I'm following correctly,
Yeah.
could offer a potential explanation for dark energy,
You got it.
the force driving the universe's accelerated expansion.
It's like this one concept, the quantum tensor field,
Right.
has the potential to unlock solutions to some of the biggest mysteries in cosmology.
It's almost too good to be true.
It is amazing.
But as you said earlier,
Yeah,
it's still a very new theory.
it is.
There's a lot more work to be done before we can declare it a definitive answer.
Absolutely. But the beauty of science is that it's a process of constant exploration and discovery.
Of course.
Theories like this one, however groundbreaking they may seem,
Mm-hmm.
are just stepping stones on our journey to understanding the universe.
And what an incredible journey it is. After diving into all this, I'm struck by how this theory challenges our very perception of reality.
I agree.
We're used to thinking of gravity as this force that acts on objects,
Right.
but the quantum tensor field suggests that it's much more dynamic and interconnected than we ever imagined.
It's a humbling thought, isn't it?
Yeah.
To realize that we might be surrounded by this invisible field that influences everything shaping the cosmos in ways we're only beginning to understand.
It's like there's this whole hidden layer of reality that we're just starting to glimpse.
It is.
And who knows what other surprises await us as we continue to explore.
I'd say that's a perfect note to transition to the final part of our deep dive. We've explored the science, the experiments, the comparisons with other theories.
Right.
But perhaps the most profound question is, if this theory is proven correct, what does it mean for our understanding of the universe and our place within it?
Yeah, it really makes you think about what it all means.
It does.
If this quantum tensor field is real,
Right.
it's not just some scientific discovery. It's like a shift in our whole worldview.
Absolutely.
Yeah.
For centuries,
Yeah.
we've been trying to understand the universe
Right.
based on what we can see,
Uh-huh.
what we can touch.
Right.
But this theory is suggesting that there are these entire layers of reality,
Right.
these subtle fields and vibrations
Yeah.
that are shaping the cosmos in ways we never imagined.
It's like suddenly realizing there's a whole conversation going on around us
Right.
that we've been completely deaf to.
That's a fantastic way to put it.
Yeah, and it makes you wonder,
Yeah,
what else are we missing?
exactly.
What other
It's-
unknown unknowns are out there just waiting to be discovered?
Exactly.
Reading about this theory,
Mm-hmm.
it's kind of triggered an existential crisis for me.
Oh, really?
If
Interesting.
we're surrounded by this invisible field that's so
Yeah.
fundamental to the universe,
Right.
what does that say about our place in it all?
It is a humbling thought.
Yeah.
It reminds us that we're just like
Yeah.
a small part of something,
Yeah.
much grander and more complex than we can comprehend.
And yet we're capable of understanding it,
Yeah.
at least to some degree.
Yeah.
We can develop these theories, we can build instruments,
Right.
and probe the deepest mysteries of the universe.
It is amazing.
It's pretty amazing when you think about it.
It really is.
And who knows what the future holds?
Exactly.
If we can figure out how this tensor field works, how to harness its power,
Exactly.
it could open up possibilities that we can barely dream of right now.
It really could.
I was just thinking about that.
Yeah.
Imagine if we could manipulate gravity, control its strength,
Right.
even create artificial gravity fields.
Yeah.
It'd be a technological revolution unlike anything we've ever seen.
I agree.
Think of the implications for space travel.
Oh, exactly.
We could travel to distant stars,
Yeah.
explore other planets,
Mm.
maybe even build entire space colonies
Right.
with their own gravitational environments.
It's incredible to think about.
But let's not get ahead of ourselves. There's
Yeah.
still so much research and testing to be done
Yes.
before we can even know if this theory is correct,
Right.
let alone start harnessing its potential.
Of course, that's the beauty of science.
Yeah.
It's a journey of discovery,
Right.
a process of constantly pushing the boundaries of what we know.
And even if this particular theory turns out to be wrong,
Yeah.
it'll have spurred new research,
Right.
new ideas,
Yeah.
and ultimately brought us closer to a deeper understanding of the universe.
Absolutely.
I think that's what I find so inspiring about all this. It's not just about finding the right answers. It's about the pursuit itself,
Yeah.
the constant questioning and exploration.
I agree.
I think that's what we've tried to capture in this deep dive,
Yeah.
to share that sense of wonder and excitement about the unknown.
Exactly.
So for all of you listening out there,
Yeah.
hopefully this has sparked your curiosity
Right.
about the quantum tensor field
Right.
and the mysteries it attempts to solve.
Yeah.
Maybe this has inspired you to do some further research,
Mm-hmm.
to dig in a little deeper into the world of theoretical physics.
That would be great.
Because ultimately, the most important takeaway is this.
What's that?
The universe is far more strange and wondrous
Yeah.
than we ever imagined.
It is.
And the journey to unravel its secrets is one that we're all on together.
That's right.
Thanks for joining us on this deep dive.
Yeah. Thanks for listening.
We'll see you next time. Ready to explore another fascinating corner of the universe?